Hola a todos, muchas gracias por mantenerse conectados. Estaremos viendo la presentación de un profesor de la Universidad de Samara y quien también está conectado, así que si tienen preguntas al final pueden realizarlas, él con mucho gusto las atenderá.
Good day. My name is Ilya Kudryavtsev, and I am going to discuss some issues concerning space electronics. What does it mean, space electronics? Does it mean that these electronics should operate in vacuum and in a broad temperature range? Or maybe it's just the electronics on board our satellites? In fact, both. Typical electronic systems in our satellites could be divided in several groups. First of all, power supply. Power supply, of course, absolutely necessary. If your satellite has no power supply or its system malfunctions, your satellite is just a brick in the orbit. Collection, processing, and storing the data is typically a main target function of your satellite. Communication is also important unless your mission does not imply that your satellite returns to the Earth. Otherwise, you definitely need communication to transmit commands and obtain data. Auxiliary functions can comprise attitude control or maybe deployment functions or something else. Being power expert is extremely useful for the engineer responsible for the satellite function. Actually, all the systems of a nanosatellite has something concerning power. So some power elements are very important in every subsystem. Primary power sources create power, create electric power from the sun if it is a solar battery, or from its chemical structure if it is a chemical source. You should know that chemical sources could be of two types: rechargeable batteries or accumulators, and non-rechargeable batteries, which cannot be recharged. Fuel cells and thermoelements are sort of exotic, however, sometimes they could be useful as well. Solar cell is a diode. Actually, it is a diode with a transparent cover. So, solar sun in form solar light in form of quantas called photons penetrates into this solar cell and produces uh, two charge carriers, electron and a hole. These charge carriers move to the electrodes, negative and positive, creating what we call electromotive force. Of course, this electromotive force is not that high. However, multitude of photons create more power. We definitely need minimum of reflection, so anti-reflection layer is used. Typical efficiency of a solar cell rarely exceeds 30%. Several solar cells should be combined somehow to create a solar battery. So you can connect these solar cells in series. In this case, you have better, higher voltage. However, non-uniform illumination can reduce the efficiency of the system. Or you can connect them in parallel. In this case, you increase overall current, but the voltage is still low. In practice, satellite engineers create something to say which we can call a trade-off. So you can see here that several groups of solar cells connected in series are connected in parallel. Diodes here are necessary to prevent reverse current from one group to another one. This is a solar panel, typical example, used by Finnish engineers in their all-to-one mission. Of course, you want to get maximum power of your solar battery. To do that, you should track what we call maximum power point. You can see that here. Maximum power point could be achieved if your solar battery has a specific load. So converters at the output of your solar battery tracking maximum power point a very good solution for getting more efficiency from your battery. This is a very simple example of power system. You can see here a solar battery, rechargeable battery, working in combination. When your solar battery is highly illuminated, it can provide power for the load and even charge your rechargeable battery using a block called charger. Otherwise, your rechargeable battery works and create current to the payload. In both cases, we use DC to DC converter to make your output voltage at the load stable and the voltage level necessary for a certain mission. What kind of regulator is better? We have two types of regulators: linear ones, linear regulators, and switching regulators. You can see here that switching regulators have better efficiency, higher efficiency, and it can be used in a wider voltage range. Linear regulator is only buck converter. It can only reduce input voltage, and switching regulator can be buck boost or even buck boost. So it is more flexible. The disadvantage of a switching regulator is some ripple and noise. However, engineers are able to inhibit this effect to a required level. Typically, we use one of these three configurations or topologies of DC to DC converters. Buck converter, where output voltage is lower than input voltage. Boost converter, increasing voltage. And inverter. Inverter is used when you need to change the polarity of your primary voltage. Let's look at the operation of the boost converter. The first phase is started when we put our switch into on position. In this case, all the input voltage is applied to the inductor. The current in the inductor is growing and the power is accumulated in its core. In this phase, output voltage is supported only by the capacitor, and this voltage, this capacitor is not discharged via the switch because the diode blocks it. At the second phase, we disengage our switch. It is now off. So input voltage and the inductor are connected in series and they provide power to the output. The diode is now open. So the capacitor is charged and the current through the inductor is going down. The power from the core is given to the output. Then the process is repeated. SEPIC converter is a bit more complicated. It has two inductors. It could be used in a buck boost topology. Buck boost topology is flexible. Manipulating by the switch, you can get buck mode or boost mode, and it is useful when your input voltage is varying in a high range, in a wide range. Of course, we do not create these DC to DC converters every time from scratch. We have enough integrated circuits which has different parameters, and they are intended to support different topologies. You can see here several solutions. In practice, you just need to select the proper integrated circuit for your selected topology, for your selected current and voltage and so on, and then just to create a circuit like shown here with a few external components, typically inductor, diode, and some resistors and capacitors. Having linear and switched converters, we can create some combined solutions. These combined solutions can use high efficiency of switched topology, switched converter, and high linearity, low ripple, and high stability of a linear converter. So several topologies are possible, for example this one or that one. There you can see that efficiency depends on switched capacitor, and high stability is achieved by low dropout linear regulators. Low dropout linear regulators have low voltage difference between its input and output, so it is more efficient than typical linear regulator, and in combination with switched mode regulator, it can create good overall efficiency. Of course, only linear regulators does not provide high efficiency, and it is reasonable to use them only if the efficiency is not a key problem or your payload does not require much current. You can see also several integrated circuits able to support MPPT, maximum power point tracking. So these integrated circuits are good for the power supply system using solar battery. Chemical power sources are also necessary. Just recall that you can use rechargeable or non-rechargeable batteries. If you need non-rechargeable batteries, typically you use them in two cases. First case is when your payload is not high. I mean that you need low current during a long-term operation. In this case, it is useful to apply lithium batteries in your power system. Lithium batteries, they are better than other types in this case because they have a low self-discharge. They can support operation during a very long time. In this case, its power capacity is not that important, and these batteries are typically used for clocks or something like that, and you can use only 50–60% of their overall capacity during a life term. In case you need more power, you can use, for example, alkaline batteries. In this case, you spend 80–90% of the capacity, but in short term. There were several missions even without solar batteries, working for months or so, only using chemical non-rechargeable batteries. In case of lithium batteries, typically your selection is between BR type and CR type. You can see that BR type is maybe better for long-term missions. It has a wider temperature range and less maybe self-discharge. What concerns rechargeable batteries in space missions, two types of these batteries are typically used. Lithium, either polymer or ion, including phosphate, or nickel metal hydride batteries. In this diagram, you can see that most part of solutions include lithium batteries or nickel cadmium as shown here. I must say that nickel cadmium batteries are maybe obsolete because of their memory effect, unwanted operational feature, and you should also know that cadmium is toxic. So toxicity is not greeted in our world now. Lithium polymer batteries reveals best efficiency of the class of such batteries, rechargeable batteries. You can see that the battery produces high voltage and has good capacity. At least our smartphones and mobile phones mainly use these type of batteries. The drawback of these batteries with regard to space exploitation is that it can get inflated in vacuum. However, this inflation can be prevented mechanically if you put the battery in a case preventing this inflation. Lithium batteries are charged in two stages. In first stage, you use current source. So current is permanent, the voltage is growing. Then, at the second stage, after approximately 80% of the capacity is charged, you use voltage source. So you provide permanent voltage at the terminals of your battery, and the current is going down. The end of the charge is determined when the current gets lower than the threshold. You should remember that overcharging and over-discharging of these type of batteries is harmful and even dangerous. Again, you can see here a complete solution. This complete solution is based on a specific integrated circuit. This solution is complete because it is a whole system of providing output voltage. In case you have input voltage, it is provided to the output. If the power is enough, some part of this voltage is used to recharge your battery. If You have no input voltage. For example, your solar battery is not illuminated. This track is closed and your battery is discharged to the payload. So maybe is a good way of doing things for a nanosatellite mission. Data collecting and processing, as I told you earlier, maybe is the main target mission. So you should know several issues. The main concept is transparent and straightforward. Typically we use analog sensor, source of the information. Analog signal is conditioned, at least filtered and amplified, and applied to the ADC, analog to digital converter. Then it is digitized, processed in digital form, and if necessary, it can be returned to the analog form using DAC, digital to analog converter, and reconstruction filter. Otherwise, you just have digital information. First issue to pay attention is sampling. Sampling means that you substitute continuous waveform by a set of samples. These samples should be taken using some device, typically sample and hold, and this sample and hold follows Nyquist criteria. Nyquist criteria can tell you how many samples do you need, or better to say, what is the sampling frequency necessary to get full information from your sensor without information loss. You can see here that sampling frequency should exceed doubled analog frequency. This F with subscript A stands for the maximum frequency in the spectrum of your analog signal. You can see here how it could be done. This case is case when Nyquist criteria is not met. You can see here the digitized signal maybe has a form similar to the analog signal, but the frequency is obviously different. So in this case we lose some information. Of course, many samples are better. However, excess number of samples is also bad solution. We don't need much more power than needed to process the signal. ADCs could be used as a frequency converter. In fact, we are talking about the effect called band aliasing. This band aliasing means that several signals of different various frequencies can be converted to the same analog frequency. So interferences and noises outband in relation to your signal could be added and reduce efficiency, reduce signal to noise ratio. That's why we use anti-aliasing filter, limiting our frequencies at the input of your ADC to the desired bandwidths. Quantization is also an issue to understand clearly. You can see here a transfer function for ideal 3-bit ADC. It is it could be seen that several signals in this stage are just transmitted or converted to the same code. So to increase resolution, you should have these stairs as narrow as possible. You can also say that the ADC having this staircase, this transfer function, adds some noise called quantization noise to the input signal. So the higher your resolution, the more narrow is the steps of your transfer function. Typically, resolution could be limited by this noise, and you can see here that we have a metric called signal to noise ratio that depends on the number of bits. You can improve the situation using oversampling. So if you have oversampling, you can increase your signal to noise ratio with this element. Having wider bandwidths, of course, means more efforts for processing. However, it is a way of doing things. Real ADCs have also their own, to say, problems. Real ADCs have some internal errors, like offset error and gain error. Offset error means that the result of quantization is always several, to say, steps or microvolts lower or higher than the real value. And the gain error means that the error deviation between real value and quantized value depends on the value itself. Of course, these errors could be compensated algorithmically. The main problem of ADCs is non-linearity. So transfer function is not linear. So in datasheet you can find this value called integral non-linearity. It is the maximum deviation of the real transfer function from ideal one. Unfortunately, various manufacturers has different ways of measuring it. So selecting your ADCs, you should be very attentive and compare not only the values in the datasheet, but also having in mind that these values could be obtained by different methods. What types of ADC do we use? There are several different types of ADCs, but in practice engineers use 3 of them. So successive approximation register ADC, pipelined ADC, and sigma to delta ADC. Which type is better to use in your satellite, in your mission? It depends, of course, on the mission itself. You can say that if you have requirements of very high resolution, your solution is delta sigma. If you need to digitize high frequency wideband signal, you use either SAR or pipelined ADCs. Of course, certain selection highly depends on your mission, on your parameters, on the number of signals, etc. Besides ADC itself, your data collecting system should have some additional elements. For example, ADCs need voltage reference source, and you need also clock source for the ADC. Sampling is performed by sample and hold. Actually, this signal is also going here as well, but it depends on a certain integrated circuit. What types of voltage reference are available? At the moment we use band gap voltage sources, buried Zener, or specific XFET elements. You can see here their parameters. Band gap are more popular, buried Zener has better noise, and so on. Again, selection of your voltage reference depends on the ADC you use and the desired required parameters of your system as a whole. You can see here that your resolution, your final resolution, depends on the temperature. And if you want, for example, 8-bit resolution and the temperature of your EDC changes about not higher than 20 degrees centigrade, it is enough more or less to have a reference with about 200 ppm over 1 degree centigrade. But if you need 16 bits, you need much more better reference. So selection of a proper reference could be a real problem. It is just an example of such selection. You can see here several chips, and you can note that some of them are rather expensive, and their parameters are very excellent. So typically we use maybe 12, 14 bits of resolution, and you should take into the consideration that your reference can really affect your overall parameters. Next problem is jitter effect. It is maybe very important if you are dealing with a wideband signal. You can see here that if your clock is not stable, I mean that you have jitter, so the edge is not stable, it means that the movement of your samples are also not stable, and the time deviation is transmitted to voltage deviation. So clock jitter will create voltage noise. Next issue concerns analog signal conditioning. There are several purposes and requirements shown here. So amplification, impedance matching, filtering are the tasks of your conditioning. How can you amplify and filter your signals? Typically that could be done by operational amplifiers. These requirements are the requirements with which you select the proper integrated circuit, proper topology of your circuitry for this conditioning. Operational amplifier is a differential amplifier with a high gain. Its differential input allows us to have good noise suppressing mitigation, and at the moment we have more than, I don't know, 10,000 types, not types, but models of operation amplifiers, so selection could be interesting. There are two main circuits of using operational amplifiers. This is non-inverting circuit and inverting circuit. What is better? Which one is better? What should you know? First of all, non-inverting topology means that the signal at the output have the same polarity as the input signal. In the inverting topology, it is opposite. You can also say that inverting topology turns your phase, the phase of your signal, by 180 degrees. The input impedance of the non-inverting circuit is close to infinity. It is defined by the amplifier itself. In case of inverting topology, the input impedance is equal to this R, to this resistor in this circuit. Gain of the circuit, of inverting circuit, could be arbitrary, less than 1 or more than 1, and the gain of non-inverting circuit is always exceeds 1. Real amplifiers have a lot of sources of error. If you are working with measurement and you need the high resolution, this conditioning circuit and the parameters of your amplifier are also very important. What should you take into your consideration? First of all, offset voltage. Then input currents. You can note these input currents does not depend on the signal. These are parasitic currents on each input of the amplifier. Then we have specific common mode error, and you should see that all the parameters are not stable. They depend on temperature, on power supply voltage, and we have also aging. Nobody is going younger, and the amplifiers also are aging. So if you are thinking about a mission to Jupiter, you should take this into account as well. In case you use low voltage circuitry, you need rail-to-rail amplifiers. Rail-to-rail amplifiers are able to amplify the whole range of your input voltage close to ground and power supply. Typical non-rail-to-rail amplifiers have some distortion when your common mode, when your signal on the input is close to the supply voltage. Sometimes we are dealing with bridge sensors. Typically these are specific sensors of some physical values like maybe temperature, force, some chemical sensors and so on. You should know that these bridge sensors have internal structure shown here. So these sensors have differential output. They have two outputs, and you have approximately 1/2 of supply voltage on both outputs, but these outputs are not in balance, and the difference could be several microvolts. So your instrumentation amplifier must not amplify this background voltage, I mean common mode voltage, and must select and amplify only this difference, this imbalance of the bridge. For that purpose, we need specific amplifier. The gain of these amplifiers is defined by a specific resistor or maybe digitally. And this class of amplifiers is also useful for many cases. You can see here some examples, some topologies using very popular instrumentation amplifier AD623 in dual supply or single supply configuration. Again, this RG is specific resistor. Changing it, you can achieve different overall gain. Interference. Interference is maybe one of the most important and most complicated issues engineer is dealing with. First of all, nanosatellite interference. Nanosatellite interference is very important when you create your circuit with flip-flops, registers, memory, and microprocessors. So always. Let's look at the topology above. This nanosecond source is just a source of very short pulses, and these pulses can get into the input. Let's look how this current of the nanosecond interference can go via block number 3 via common wire to the ground. So this current is flowing via this part of common wire. It has inductance, it has resistance, and some voltage drop on these inductors and resistors is actually applied to the input of blocks number 1 and number 2. If there are flip-flops, memory, or microprocessors inside, they can have an error, even get into hang-up mode. How we can prevent that? Just put your ground in this way, as shown here. The way of nanosecond interference is now different. It does not go to the common wire where it is dangerous. So the golden rule of preventing nanosecond interference: just don't allow this interference to flow in the dangerous part. Practical example. Look here, we are dealing with a very important circuit for a microcontroller. You can see that it is a typical circuit of an oscillator, a clock oscillator for the microcontroller. Let's look at the topology number 1. We have a ground wire, common wire, and definitely nanosecond interference can go through this part of the wire. If some nanosecond interference is here, it can be applied between this point, and this point. What does it mean? It means that we have a spike like this in our clock signal. The situation is crucial for the microcontroller operation. Many of them can hang up. Look at the topology number 2. We connect capacitors and the ground by one specific appendix. There is no need of the interference going somewhere to get here. So we do not allow this spike to appear into our clock signal. So this is a way how we can inhibit our nanosecond effect. Next type of interference is surge. Surge has much power and it can even destroy your components. The main idea how to prevent this situation is just to use some elements absorbing the power of this surge. For example, this type of diode is just a suppressor. They can absorb the power of the surge coming to the electronic module. You can use transil diodes or even trisil diodes. You can see the difference here in their IV curves. Trisil diodes absorb more power, but they are less popular. At the moment, our industry provides a lot of many types of these transil diodes. They can absorb powers about even a kilowatt, of course, in short pulses. Again, an example. If you have two topologies, this topology is much more better than that. Or vice versa? Of course not. Look at the topology number 1. Suppressor T1 is connected to the integrated circuit. Actually, T1 is here just to protect IC1, but there is an inductance. You connected your suppressor with the circuitry by the long trace. This inductor is harmful. It will interfere, it will affect the suppressing ability of T1. In this number 2 topology, T1 is connected by a wide trace and short trace, so its efficiency is much more. Using suppressors, using these transil diodes, you should take it into the account. Traces connecting suppressors and the victim and source should be as short and wide as possible. Otherwise, parasitic inductances and capacitances sometimes can make your suppressor useless. Electrostatic discharge is maybe very specific. It can create a problem for your satellite before the launch. The reason why it is so that the source of electrostatic discharge problem is a human. Is engineer or I don't know somebody who contact components and the PCB, your device and so on during assembly. So we have a lot of components which can be destroyed or maybe in general for which electrostatic discharge is specifically dangerous. So this label marks these types of components. You can see here that ESD impact could destroy wires inside your integrated circuit. You can see here that in this case the integrated circuit is not destroyed. We still have some trace. But the reliability of the circuit after this impact and the life term of this circuit is a problem. It is in question. ESD can create a short current or just can destroy some traces or whatever. And at the final type of our discussion, several words about passive components. Capacitor types are maybe the most problematic components, and you should keep that in mind. Typically, we use 3 types of capacitors in our circuitry: ceramic capacitors, electrolytic capacitors, and some type of film capacitors. Maybe speaking more generally, capacitors with organic insulator inside. Which parameters of these capacitors are important? First of all, ceramic capacitors. Ceramic capacitors are essentially fragile, so under mechanical stress they can get crack, and you can see that this crack can fully destroy capacitor or reduce its capacitance. You should know that this mechanical stress can occur in different cases. For example, during improper soldering or under vibration and other mechanical stresses. Ceramic capacitors are typically manufactured in two classes, class 1 and class 2. You can see here that class 1 is much more better. However, its capacitance is not that high as class 2 capacitors. However, we need both types. Unexperienced engineers often think that capacitor is sort of ideal and the only parameter is capacitance. That's wrong. We have a lot of different issues. For example, temperature coefficient, or its tolerance, or some kind of inductance, and so on. So coding of class 1 ceramics is shown here. You should know that even class 1, best class capacitors have different parameters. For example, NPU are the best. Class 2 ceramic capacitors have different system. They have 3-letter coding. 1, 2, 3. You can compare that, for example, X7R capacitor is much more better than, for example, Z8U. So these letters mean much. For example, you can see here several types of capacitors, and you can see that the capacitance of your element depends on DC voltage and depends strictly. For example, this I5V capacitor has about 90% deviation from the nominal. However, NPO is intolerant. Or aging, time of operation. Again, you can see that I5V can lose 20% of capacitance. Or temperature. Of course, this information about capacitors is specific. It depends on the capacitor, on the technology, on the requirements, on the mission. However, what you should understand clearly: good mission is created by an engineer who is responsible for all solutions. So you have to take into your account all the parameters of all components. All components, active and passive. All systems, data collecting, communication, etc. This is just a secret of your success. Now that's all what I'm able to discuss during that short period. So thank you for your attention. If you have some questions, I am more or less ready to answer. Так, ты меня оставил с сияющим синей бородой. Ну ладно.
Alright, thank you and welcome, teacher. Um, this is a space for questions and
Sorry, some technical difficulties. Just a minute.
yeah, for sure.
Oh, it looks better. I think my lecture was more or less interesting for you, something useful, okay? And if you have some questions, I'm ready.
Yes, there is one on the chat. I don't know if you can see it. Rocio asked what reason was taken for the sample size.
Sample size, what do you mean sample size? Sampling frequency or what?
Rocio, if you want, you can turn off your microphone and speak. Maybe if you want.
Sample size. Size of what?
Well, meanwhile, there is one question more.
You know, in Russia, internships typically does not play a very important role. I think that important internships are possible and they are useful, of course, but they are not compulsory. I mean that, for example, in master program, during these 2 years, internship can be, or but it is not compulsory. I mean that sometimes our students have some internship at a factory or in some designer company or whatever. But we cannot say that we send our students worldwide or whatever. It depends. It depends on maybe the student, on its scientific interest, and so on. So I have no universal answer for this question. However, I can say that sometimes we invite some students from abroad for some internship in Samara University. For example, if your university has this internship as a typical way of study, maybe something compulsory at your university, our university maybe the place where you can have this internship. Again, it depends on your scientific interest and so on. You need to have a contact to announce your intentions, and okay, you're welcome. Signal with the bandwidth mass sample, yes. Yes, exactly, Rocio, you are right. I mean that if you design a data collection system, and in this case, you should follow this Nyquist criteria. Sampling frequency should exceed doubled frequency of your spectrum. However, maybe you remember I have shown you some diagrams that sometimes we use undersampling. In case of radio signal has high frequency, high carrier frequency, but the information, useful information, can have frequency much less. And in this case, when you are not interested in details of carrier, you can use sampling frequency lower, maybe several times lower than Nyquist criteria requires. Yes, something else? What is the process to get started? First of all, you should know which research team are you going to join. I think you can send some information about you, about your interests, about your plans, about your expectations, and I'm sure that we can find somebody who is interested in contact, in collaboration, and in this case you can come here and work with us to develop something what is interesting for you. First step is to send us something about your interests.
All right. Thank you very much, Professor. I don't know if someone else have questions. If that is not the case, maybe we can finish with this presentation and to start with the other one. Thank you to be with us today. Thanks. See you in another time. Maybe do you have some messages for people who are listening now?
I would like to say that science and engineering skill is a very specific thing. I mean that to be an expert, you should be an expert. Try to be an expert, try to study whatever you want. Don't be afraid to ask what is not understandable, what is not clear for you at the moment. And this way will lead you to the success. And of course, your professors and other professors from other university and of course from Samara University are ready to help you. Just be open and you will get what you want. So I wish you great success in your career, in your scientific engineering career, and hope that everything will be successful.
All right. Thank you very much. Goodbye.
Thank you.